Hi, welcome to video 2 for lesson 3.2. This video will look at gamma distributions. Last time we saw that in a Poisson process with a mean lambda, the waiting time until the first event occurs follows an exponential distribution with a mean theta that's equal to 1 over the lambda from the Poisson distribution. Now we'll let x denote the waiting time until the alpha event occurs. So let's draw a picture. We've got our timeline here. We can see the first event occurred, the second, the third, and so on. We have events that occurred in time. Now, if we're interested in the alpha event, and we want to know the amount of time that passed before that event occurred, and that's going to be our random variable x, just to give us an idea of what we're really modeling. X has what is called a gamma distribution. And so when alpha is equal to 1, we have the exponential, which is really a special case of the gamma distribution. The gamma distribution is determined by the parameters theta and alpha. And the probability density function for the gamma distribution is given by little f of x is equal to 1 over alpha minus 1 factorial times theta raised to the alpha power, multiplied by e to the minus x over theta times x to the alpha minus 1 for values of x that are greater than or equal to 0. So we've got another continuous probability distribution here. Now there's a special function called the gamma function. It is defined as gamma of t is equal to the integral from 0 to infinity of y to the t minus 1 times e to the minus y dy for t that are greater than 0. And if t happens to be a positive integer, it can be shown that gamma of t is equal to t minus 1 factorial. So often that alpha minus 1 factorial is replaced in the gamma distribution by gamma of alpha. And so we rewrite the PDF of x as f of x equal to 1 over gamma of alpha times theta to the alpha multiplied by e to the minus x over theta times x to the alpha minus 1 for values of x that are greater than 0 or equal to 0. And so this is how we usually see the gamma distribution written with the gamma function. It's how we get our name of the distribution. The moment generating function for the gamma distribution, m of t, is equal to 1 over 1 minus theta t raised to the alpha power for t less than 1 over theta. The mean and variance for the gamma distribution are the mean mu is equal to alpha times theta, so that's the number of events, multiplied by the number of events that we need to occur. So that makes sense. And our variance, sigma squared, is equal to alpha times theta squared. And the derivation of these formulas is all shown in the text. I'm not going to go through it all here because it's very long and sort of mathy, and I'm not sure how much people really want to see that. But if you do want to see somebody walk through the derivation, just let me know and I'll be happy to make a video that does that. Let's take a look at the effect of changing theta on the gamma distribution. So remember, theta is the mean time until the first event. So it makes sense that the time until the alpha event, here we have alpha equals 3, so we have the time to the third event, is going to be longer on average when we have a larger value of theta. And we can see we've got skewed distributions. And if we change the value of alpha, so now we're saying, okay, we want to see different number of events occurring. Here I'm choosing a constant value of theta. So the average time to the first event is 3. And we can see the effect of changing alpha. So if we want to see more events, our distribution gets shifted more to the right. And notice that when alpha is equal to 1, that is actually an exponential distribution. So let's take a look at an example. Suppose that at your favorite fishing spot, you catch on average 1 fish every 20 minutes, and that the number of fish caught per hour follows a Poisson process. You want to catch 2 fish for tonight's dinner, and we're going to let X be the time it takes to catch the 2 fish. So the things we're going to do, we're going to find the PDF for X. We're going to find the mean time you should expect that it will take to catch, sorry, I typed 3 there, but it should be 2 fish, and the variance and the probability that it will take between 1 and 3 hours to catch the 2 fish. So I'm going to just scribble out here. Sorry about that. Okay, so let's work through this example. So we know that if we're catching a fish every 20 minutes, that means we're catching 3 per hour. So our Poisson process has a lambda of 3. And since theta is 1 over lambda, our theta here is 1/3. We're interested in the time to catch 2 fish, so alpha is equal to 2. Now, if we want to find our probability density function, we take our formula and we substitute in 1/3 for theta and 2 for alpha. And if we simplify, that gives us 9x e to the minus 3x, and that is our probability density function for x. Now, part B, we're going to find the mean time we should expect it will take to catch 2 fish. We know that the mean is equal to alpha times theta. Since alpha is equal to 2 and theta is equal to 1/3, we multiply those together. It gives us a mean of 2/3, or about 0.6667. Now if we want to find the variance is given by the formula alpha times theta squared. We take 2 times 1/3 squared, and that gives us 2/9, or approximately 0.2222. And this brings us to part D, where we're going to find the probability that it will take between 1 and 3 hours to catch 2 fish. We have our probability density function, f of x equals 9x e to the minus 3x, and we are going to integrate from 1 to 3 that probability density function to find our answer. Substituting in our probability density function and doing our integration, evaluating it at 3 and 1, taking the difference, gives us a probability of 0.1979. Coming in our next video, we'll take a look at the chi-square distribution, which is really a special case of the gamma distribution that is extremely useful in many statistical tests.